In this video, we're going to do an example using the Gram-Schmidt process with inner products. So in this example, let's define the inner product of f and g to be this integral from negative pi to pi of f of x times g of x. So we're defining this as an inner product on the vector space that consists of infinitely differentiable functions. So functions that we can take the derivative of an infinite number of times. And we commonly denote this as C infinity. If we let W be the span of sine x and x, we want to find an orthogonal basis for W. Alright, so that is the problem that we're tasked with. So before we get into doing this, at some point in doing this problem, we're going to need to do some integrals, some antiderivatives. So I want to do a brief review of even and odd functions because they're going to show up and help our computation. So a review of even and odd functions. Okay, so a function f is odd when f of negative x equals negative f of x. And a function f is called even when f of negative x equals f of x. So graphically, let's draw a graph of an odd function and a graph of an even function. So an odd function graphically ends up being symmetric about the origin. So I'll draw an example of what that looks like. So symmetric about the origin means it might look something like this. Maybe it does something on one side of the origin, but whatever it does on one side of the origin, on the other side of the origin, it'll sort of be like the mirror image of that through the origin. So for example, if I look at this point and I draw the mirror image of that through the origin, that mirror image would be somewhere over here. So we'd be doing that for all the points on this blue curve. If I draw the mirror image of all of them, we get something like that. And that's what our graph would look like. This is symmetric about the origin. So in terms of the formula, what this says is when we plug in negative x into our function, and when we plug in positive x, those outputs, so what f of negative x is, and what f of x is, they need to be opposites. That's why there's a negative sign here. And that's what's happening in this graph. So on the flip side, with even functions and their graphs, so if I draw an xy axis, and with an even function, these are symmetric about the y-axis. So I'll draw an example. So something that's symmetric about the y-axis might look something like this, and then I draw the mirror image on the other side of the y-axis. That'll look like this, drawing its mirror image. So in terms of the equation with this one, when we plug in some positive x value, and then we plug in its corresponding negative version, this equation is saying that f of negative x and f of x better be the same. In other words, their outputs, the output when I plug in negative x and the output when I plug in positive x, need to be the same. That's why it ends up being symmetric about the y-axis here. So the key things that I'm going to want to use in our example that'll show up is when we have an odd function, and when we integrate it from a negative value to its positive, corresponding value a, that ends up being, I forgot to write the dx. Let's put in the dx. That ends up being 0. Because if I look at my graph visually, whatever this area is, that's going to cancel out what the area is going to negative x. That's why that's 0. Well, with an even function, when we do the same thing, if we take the integral from negative a to positive a of an even function, then they don't cancel each other out. Instead, what ends up happening is we could look at just the integral from 0 to a of our function, and we end up doubling it. So we have to multiply by 2, because whatever the area is on the right side of the origin, we get the exact same area on the left-hand side. So that's why it gets doubled here. Whereas with odd functions, they end up being opposite, and that's why it cancels out and we get 0. All right, so let's get back to our example now. So here's our example one more time. So we were trying to find an orthogonal basis for w, and w is the span of sine x and x. So if we look at this set, sine x and x, those two functions, well, these two functions are not multiples of each other. They're not scalar multiples of each other. So this is linearly independent. If we have two elements in our set, it's linearly independent if they're not multiples of each other. And we already know that those two functions span w, because that's how it's defined. And this set spans w, so it's a basis for w. So it's a basis for w. So a natural question is, well, what if this is already orthogonal? Well, then we'd be done. So first, let's check if it is orthogonal, if our set is orthogonal. Okay, so to do that, we need to take the inner product of these two functions. So let's take the inner product of sine x with x. So using our definition of the inner product, we got to take the integral of the two functions multiplied from negative pi to positive pi. So here we're going to have to take the inner product from negative pi to positive pi of x times sine x. Our two functions multiply. All right, and now we need to evaluate what this integral is. So at this point, this is some calculus review. Pause the video for about 30 seconds and see if you can remember what is the technique that we use to integrate this. Just the technique. Don't worry about doing the whole thing. Just see if you can remember what the technique is. So 4, 3, 2, 1. Pause the video. Pause the video for about 30 seconds and see if you can remember what is the technique that we use to integrate this. So we need integration by parts for this. So let's start to write down all the pieces of this. So, sorry, no vector here, just integration by parts. So if we do integration by parts, we'll let u be x, because it has a very simple derivative. Du would just be dx. We'll let dv be the sine x dx. So its antiderivative, v, is negative cosine x. Okay, so that's my integration by parts setup that I want to have. So integration, we're doing integration by parts here. So we use it really often when we have something like a polynomial term, like x, multiplying like a trig function like this, or multiplying an exponential function. It's not the only situation where we use it, but that's one situation where we use it. Okay, so let's apply this now. So I want to apply integration by parts, but there's one other thing that I want to keep in mind before I dive into this, which is I did that review on even and odd functions. Let's not forget that. Let's first determine if this function is even or odd. Alright, so let's do this on the side here. So if we think about, if I just call this function maybe like h of x is x times sine of x. So to determine if it's even or odd, we can plug in negative x into it and see what it gives us out. So that'll give me negative x and then times sine of negative x. But sine is an odd function. And just to review a little bit, cosine is an even function. Cosine is an even function. So as a result, So we have the negative x in front, but sine of negative x, because it's an odd function, will be negative sine x. So the negatives cancel, and I get x times sine x. But that's just the same thing as h of negative x. Sorry, that's the same thing as h of x. My mistake there. Same thing as h of x. So we got that h of negative x equals h of x. That means this function is even. We have just shown that this function is even. And using our review, when we integrate an even function, now we know this is even, from negative a to positive a, that's the same thing as just integrating from 0 to a, our function. But we got to multiply it by 2. We got to multiply it by 2. And it'll turn out that this will just simplify the computation a little bit, because 0 is a nicer number than negative pi, and I'll be less likely to make mistakes. So that's why this is a nice thing to do. All right, so now let's apply integration by parts. So we have this 2 in the front, and now when we do integration by parts, we first write u times v. So that's negative x times cosine x. I got to apply my limits of integration, which are 0 and pi here. And then minus the integral 0 to pi of v du. So that's negative cosine x dx. All right. So continuing to evaluate this, we have this equals 2 times, so we have negative x cosine x. We'll need to plug in 0 and pi into that. But let's figure out what this antiderivative is. So the double negatives here will cancel. Double negatives will cancel. And the antiderivative of cosine is just sine. We have plus sine x. And with the sine x, I also have to plug in 0 and pi into it. But when we plug in pi and 0 into sine, both of those are just going to be 0. So this will just become 0. All right. So now we need to plug in pi and 0 into negative x cosine x. So we have 2. Plugging in pi, we get negative pi times cosine of pi. And then minus what we get when we plug in 0. But if we plug in 0, we'll get 0 times something, and that's just 0. All right, so we have 2 times negative pi, and cosine pi is negative 1. So we have 2 pi. So 2 pi. So 2 pi is what sine x and x, their inner product was. So it's not 0, so we didn't get lucky in the fact that our two functions are not orthogonal right off the bat. So at this point, we know that sine x and x are not orthogonal. And because they're not orthogonal, well, that means now we use Gram-Schmidt. So let's do that. So now let's use Gram-Schmidt. I'm just going to abbreviate it as GS. Use the Gram-Schmidt process. Gram-Schmidt. Gram-Schmidt to form an orthogonal basis for W. Orthogonal basis for W. Alright, so when we do Gram-Schmidt, so let's recall what our two functions were originally. So we had a function, I'll call the first function f of x. So I'll let that be sine x, that was one of our functions. And the other function, I'll call it g of x. And our other function was just x. So when we do Gram-Schmidt, we introduce new variables for our new things. Usually with vectors, we call them like v1 and v2. With functions here, I'll call them f1 and f2, and so on. So f1 of x, using Gram-Schmidt, is just our first thing. So our first, in this case, function, which is f of x. And that's going to be just sine x. So it starts off simple like that. The first, in this case, orthogonal function is just going to be my first function in my linearly independent set. And then f of 2, f2 of x, will be the second function in our linearly independent set, that's g of x, minus the projection of f of x onto the span of f1 of x. And I'm sorry, I meant to write g of x here. So I want to project this second function in my independent set g of x onto the span of the previous orthogonal, in this case, functions. So that's why I'm writing f1 here, span of f1, and not just the span of f. Alright, so now let's evaluate what this is. So we have g of x, and we've stated a formula for the projection in a previous video. This is going to be the inner product of g of x with f1 of x divided by inner product of f1 of x with f1 of x times f1 of x. Alright, so now let's start to evaluate these things. So we've already done the inner product in the numerator, because this is, so g of x is x, f1 of x is sine x. We already did that inner product. We know this is 2 pi. That's the one that we just did above. We know that that's 2 pi. So we need to do this inner product in the bottom. Let's do the inner product of f1 of x with itself. So f1 of x is the function sine x. So we need to take the integral from negative pi to positive pi of sine x times itself. In other words, sine squared x. Sine squared x. Alright, so sine squared is an even function. This time I'm not going to show why. I'm just going to go ahead and do the computation using the fact that it's even. But I'd encourage you to pause the video and check it like we did before if you're unsure why it's even. So then we'll get the integral from 0 to pi of sine squared x. And we put a 2 in front, and we have this dx. So now we kind of have to go into our trig integrals bag. So there's a trig identity that we need to use to integrate this. So we have the 2 in front, integral from 0 to pi. Sine squared is the same thing as 1/2 times 1 minus cosine of 2x. That's what sine squared is. So sine squared is this right here. So now we can distribute the 2 in, and we get the integral from 0 to pi of 1 minus cosine of 2x dx. And now this integral is not too bad to do. So let's integrate this next. So taking this antiderivative, the antiderivative of 1 is x. The antiderivative of minus cosine 2x is going to be minus sine of 2x divided by 2. I could either do that by inspection, by looking at it, or we could do a u-sub to figure that out. Alright, and now we need to evaluate this at 0 and pi. So plugging in pi into this, it's actually before I even plug pi into this, I noticed that with the sine of 2x term, if I plug either pi into that and get sine of 2 pi, or if I plug 0 into that and get sine of 0, it's going to be 0. So this term is going to be 0 when I plug in these two values. So when I plug pi in for the x, I get pi. When I plug 0 in, I get 0, so I have minus 0. So I have pi. That's what our other inner product ended up being. So at this point, we're ready to go back to our Gram-Schmidt and write down what f2 of x is. So f2 of x was my second function in my original set. That was x minus the inner product of x with sine of x on the top, divided by the inner product of sine x with itself. And then this whole thing times f1 of x, and f1 of x was sine x. So recall that this is using the formula. This is using the formula g of x. Let me just go ahead and write it down, because we've seen it already. Alright, so I've gone ahead and just copied that down. So now plugging in what these inner products were. So we have the x minus the inner product of x with sine x, that was the one that we had done before. That was the 2 pi. That was the 2 pi, and we had been highlighting this in yellow the whole way through. And now the other inner product on the bottom, well, that's this pi that we just got. That's what we have on the bottom. We have pi. That was the inner product of sine x with sine x. And that's multiplying sine x, because that was f1 of x. This ends up just being x minus 2 sine x. So that's the... Alright, so our orthogonal basis had the function f1, which was just my first function in the original set. That was sine x. And then f2 is this function x minus 2 sine x that we got using the Gram-Schmidt process. Alright, so the key takeaway from this is we can do things like the Gram-Schmidt process, least squares, orthogonal decomposition, best approximation. We can use all of those theories that we've developed when we talked about Rn, and we can generalize them to any finite dimensional vector space by using, any finite dimensional vector space that has an inner product.